Previously, we looked at the definition of an acid and a base by Arrhenius, a classical definition of that. And specifically, the point we pick from there is, according to Arrhenius' definition of an acid is a substance that donates hydrogen ion in solution, while a base donates hydroxyl ion, that's hydroxide ion OH negative, in a solution. Now, Bronsted and Lowry gave a generalized definition to an acid and a base, and from that definition, it was stated that an acid is a substance that donates a proton, while a base is a substance that accepts a proton. So what does that mean? Whenever there is an acid donating a base, there must be some donating the proton rather, okay? There must be some base that will be there to accept the proton donated by the acid. And that's what we have here, right? This is an acid in aqueous solution donating a proton. There must be a base there to accept that proton. Bronsted went further to state that in aqueous solution, the proton does not just exist as hydrogen ion, unlike the classical proposition by Arrhenius. Because Arrhenius' concept of acid is that in aqueous solution, hydrogen ion is being transferred, which means that a proton exists as hydrogen ion. Bronsted said no, that a proton in solution exists as hydronium ion. Because when the acid donates a proton, there must be a base that will pick this proton donated. Hence, just imagine that you have an acid donating a proton, then there should be a base that will pick that proton. If we consider water as a base in this case, for example, because most dissociation reaction takes place in what? Water. Is that okay? As a universal solvent. Now, if water picks this proton donated, we would see that the number of hydrogen there will become 3. And this is H3O positive. We refer to this as hydronium ion. So Bronsted is saying that this is the form in which a proton exists in aqueous solution. Now, we want to use the dissociation of acetic acid to understand the difference between the classical definition of an acid and, of course, a base as given by Arrhenius, and the generalized definition of an acid and base as given by Bronsted and Lowry in 1927. This is two reactions on the board where acetic acid is dissociating. According to Arrhenius, this acetic acid will donate a proton. You can see that, right? That is hydrogen ion. So we're going to have the acetic ion, ethanoic ion. Is that okay? Or you can say ethanoate ion, because this is actually ethanoic acid. By the old name, we call it acetic acid. So according to Arrhenius, this is what the product will look like. So you can see that in solution, the proton is existing as what? Hydrogen ion, according to Arrhenius. Now let us shift our thought to Bronsted and Lowry's general definition of an acid. This is same acetic acid. In aqueous solution, it's donating a proton. There must be some base to accept that proton. That's why we have water here, because you know that generally, as I stated earlier, dissociation reaction takes place in water as a universal solvent. So if the proton is donated by this acetic acid, the proton is this hydrogen atom here, right? If it's being donated, this water will pick this proton that is donated. Now, if water picks this proton that is donated, this number of hydrogen will become how many? 3. So you have your hydronium ion, and then you see that you get your acetic ion, acetic acid ion. Is that okay? Now, what's the difference between this and this? In aqueous solution, according to Arrhenius, the proton exists as what? Hydrogen ion. But according to Bronsted-Lowry, it exists as what? Hydronium ion. This generalized definition of an acid and a base given by Bronsted-Lowry is very important because it introduces the concept of conjugate acid-base pair. And how do we pick that? Remember, to every acid, there must be a what? A paired base. So let us see how it works from Bronsted-Lowry's concept. So we're going to focus on this latter definition because this represents the Bronsted-Lowry's definition of acid and base. You can see that this acid donates the proton, water picks it. Therefore, this acetic acid is serving as our acid in the reactant. Water that is receiving the proton is now serving as what? The base. That's correct. Now look at the product formed. In the product, we have the acetic ion and we have the hydronium ion. You know, this is an equilibrium reaction, so the reaction can still be reversed. You can see that. This hydronium ion can transfer or donate a proton to this acetic ion to give us acetic acid, that's ethanoic acid. And what? Water, because once one hydrogen is transferred, this will become H2O, reversing the process. Hence, look at this part. In the product side, the hydronium ion donating the proton now becomes what? The acid. That's correct. While the acetic ion accepting the proton becomes the base. So, how do we now pick our conjugate acid and base pair? Now watch and see. This water and hydronium ion will form our acid-base conjugate pair. That's conjugate acid-base pair. I'm going to write this as acid. Let this be acid 2. Let this be base 2. Is that okay? And then we're going to have this as base 1. And then this, let me use the marker for this, acid 1. So with this, you can actually pick our conjugate acid and base pair. Now watch. From the reactant, we have acid. Because this donated a proton, it gave us this base here. That is the conjugate base, right? So you can see now, acid base pair. So this will give this acetic acid and the acetic ion will give us our conjugate acid base pair. Why this water serving as a base here and hydronium ion serving as what? Our acid will form our acid base conjugate pair. Does that make sense? You pick those terms that contain something like water, hydronium, is that okay? Now, this donates a proton, giving us this base in the product. So you pick the acid from reactant, the conjugate base will now be the base in the what? Product. That's how you pick it. Does that make sense? Then if you pick the base from the reactant, its conjugate acid will be the acid in the product. Pick one from reactant, pick one from product. Pick one from product, pick one from reactant. If you pick acid from the reactant, its conjugate base will be the base in the word product. And if you pick the base from the reactant, its conjugate acid will be the acid in the product. So that's how the concept of conjugate acid-base pair goes. We're going to see more of them in the next video. We're now going to look at the relationship between the strength of an acid and their conjugate base. Following the definition by Bronsted-Lowry, the strength of an acid is determined by its tendency to lose a proton, while the strength of a base is determined by its tendency to accept a proton. It's important for us to know, therefore, that a strong acid will have a large tendency of donating a proton. And then a strong base will have a strong affinity, a large affinity for accepting, a proton. In general, summarizing this concept, if you have a strong acid, then its conjugate base will be a weak base. But on the other hand, if you have a strong base, then the acid, which is the conjugate acid, is going to be a weak acid. I'll have some example here on the board to illustrate this fact. This is the dissociation or ionization of hydrochloric acid in water. This HCl will donate a proton, that is hydrogen, to water, and then we're going to have a Cl negative, that's chloride ion, and then hydronium ion. Now if you look at this, you notice that this is a strong acid. Hydrochloric acid is a strong acid. Triazonitrate 5 acid, HNO3, is also a strong acid. Tetraoxosulfate 6, H2SO4, is a strong acid. These three are major strong acids. Take note of that, okay? So if HCl is an acid, then its conjugate base will be obtained from the product. So the base you have in the product will be the conjugate base to this acid. Therefore, HCl and Cl negative, they are conjugate acid-base pair. Hydrochloric acid is a strong acid. Therefore, the chloride ion, which is its conjugate base, is going to be a weak base. On the other hand, looking at this is the acid from the product side. Therefore, the base will be picked from the reactant. Is that not so? Or you pick the base from the reactant, and then its conjugate acid from the product. Therefore, hydronium ion and water forms a conjugate acid-base pair. Hydronium ion is an acid, and it's a weak acid compared to hydrochloric acid, of course, you know. Then water here will be acting as a strong base. Let's quickly look at this reaction. Water reacting with ammonia. Now, water will be acting as an acid here, so it will donate a proton to ammonia, giving us ammonium ion. And of course, you know, if one hydrogen is donated from here, that is, proton is donated, we'll be left with one hydrogen and oxygen, giving us OH. Look at it, hydroxyl ion or hydroxide ion. Now we can pick our conjugate acid-base pair as usual. This is our acid. Its conjugate base will be picked from the product. So OH negative will be the conjugate base to this water. It therefore means that water and the hydroxyl ion, they form a conjugate acid-base pair. Water is a weak acid, not a strong acid. Therefore, if water is a weak acid, OH will be what? A strong base. That's OH negative. In the other way around, if you pick that, say, okay, this is our base from product, and then the acid from the, okay, base from reactant, then acid from the product. Then you have that this base, ammonia, and this acid, ammonium ion, form our conjugate acid-base pair. Now, ammonium ion is a weak acid. Therefore, its conjugate base will be a strong base. In the next video, we're going to look at the Lewis definition or concept of acid and base.